In this lecture, we're going to go through an example problem for comparing and identifying intermolecular forces for a series of different molecules. And hopefully you've had a chance to try this out. I'm going to walk through this myself now, and I've got all three of them drawn out here. Um, and I have drawn these in 3 dimensions. And I think that's really important when evaluating intermolecular forces because it'll depend on whether or not the molecule is polar. And we really need to consider the geometry in 3 dimensions when we do that to make sure we're properly thinking through whether or not dipole moments cancel out. So I'm going to go through and evaluate each of these comparatively for each of our different forces. And let's start with London dispersion forces, our weakest one. So looking at all 3 of these, they're all fairly like medium-sized molecules. They all have electrons and bonds. Therefore, they all have London dispersion forces. And so I'm going to list that for each one of these because they all have it. And when you're on an exam or when you're trying to evaluate these, it's helpful to, I think, start with London dispersion forces because it gets something on paper right away. And it's like, yeah, I know that's right. Everything has it. So it's going to have London dispersion forces. Now, the next step is to evaluate whether or not the molecule is polar to determine if it has dipole-dipole interactions. So that's going to involve looking at our electronegativity values and then determining if we have any polar or nonpolar bonds. So I'm going to go through and write down my electronegativities here. Looking at my electronegativity table, I know that phosphorus is 2.1, carbon is 2.5, and hydrogen is also 2.1. So the greatest electronegativity difference here in this molecule is 0.4. So I have no polar bonds whatsoever. So it is nonpolar. So I do not have a dipole-dipole interaction, or sorry, dipole-dipole interactions between molecules. I just have those London dispersion forces. Coming on to our next one, evaluating it, our hydrogens are all at 2.1 and our carbons are 2.5. And our oxygen value is 3.5. And so I'm going to get a electronegativity difference of 1.0 between our oxygen and our carbon, and an electronegativity difference equal to 1.4 between our oxygen and our hydrogen. So I'm going to have a dipole moment that's in between both of those, or on both of those bonds, which will give me an overall dipole moment around this oxygen pointing in this direction. And since that's really only half the molecule with the dipole moment, this is going to be an overall polar molecule. And because it's polar, it can interact with other molecules like itself, where it'll line up its partially positive end of the molecule with the partially negative end of another one. So I'll have dipole-dipole interactions. All right, let's look at our last one. So I have sulfur, which has an electronegativity value of 2.5. Carbon is also 2.5, and fluorine is 4.0. So I have a difference that's larger than 0.5 between those carbon and fluorine bonds. That's 1.5. So I have little dipole arrows here. And if I kind of imagine the average of that, I'll have a dipole moment for the whole molecule that's pointing in this direction towards the fluorine. So the fluorine side of the molecule will be more partially positive, and we'll have a more, or sorry, partially negative and a partial positive charge then over on the other side. And so this one is also polar. And so that means we have a dipole-dipole interaction here. All right, the last one we're going to evaluate is hydrogen bonding. Remember, hydrogen bonding requires within the molecule itself a fluorine hydrogen bond, oxygen hydrogen bond, or a nitrogen hydrogen bond. And so let's go and look at each of these molecules for one of those 3 types of bonds within the molecule. I have carbon-hydrogen bonds in my first one, but those aren't going to have enough of an electronegativity difference to participate in a hydrogen bond um, or hydrogen bonding interaction. And it's confusing because there are hydrogen bonds. There's a bond between a carbon and a hydrogen, but it's not a hydrogen bonding interaction, which makes it really the worst name interaction of all of them because it's confusing. Now, in our next molecule, we have an oxygen and hydrogen bond right here. And so that fits our requirement for a hydrogen bonding interaction. So that means it'll be able to form a hydrogen bonding interaction here with the lone pair on another oxygen in another molecule. So we'll have H bonding here. And then in our last one, looking at it, we don't have any hydrogen atoms at all. So it's not possible to have a hydrogen bonding interaction. And be careful because we do have these fluorine, and fluorine is part of our requirement for hydrogen bonding, but it has to be bonded to a hydrogen. And this one is bonded to a carbon. All right, so now we've evaluated all three of our intermolecular forces. We can compare these. We have only one for our first molecule, London dispersion. So this will be our weakest intermolecular forces. And for our second one, we have London dispersion, dipole-dipole, and hydrogen bonding. So this will be our strongest. And our last one is just kind of somewhere in the middle. It's not the strongest, but it's not the weakest. Those dipole-dipole interactions are meaningful. But when we compare them to the hydrogen bonding that's occurring on the center molecule, then it's just not as strong.